wait about another minute, and then we'll get cracking. We're going back to the example that we started working on yesterday, just talking about the temperature dependence and the product distribution based on the temperature and all that stuff. That's what we'll be doing today. Excuse me. All right, so when we left off on Monday, we left off talking about this generic example. Sorry about that, where you have a conjugated diene and you add HBr to it, and we said that the mechanism wise that it proceeded through an allylic carbocation, right? That was the. But from that carbocation, you can get two products. You can get the direct attack product or the 1,2 product, or you can get the resonance product, which we call the 1,4. And I didn't put this in on Monday, but if you think about numbering this, since we started at this end with this alkene, we'll number it that way. So that'll make the 1,2 and 1,4 make more sense. This is direct attack, and this will be considered excuse me, resonance attack. All right. So let's go back to the example that we were going to discuss, which is right here. Just going to move this down. All right, so we're going to actually work through both of these. The example is going to go right here, but it asks about the mechanism, to show the mechanism here. So we're actually going to show that on the top page. All right, so what it's asking is at 0 degrees with HBr to draw the major and the minor products, and then at 37 degrees, draw the major and the minor products. And so what, in essence, what we're doing is with the major and minor are going to flip-flop based on the temperature, right? So at low temperature, you're going to see more of the 1,2 product. So low temperature, the 1,2 product is going to be your major product. And then at higher temperatures, the 1,4 product is going to be major. All right. So let's go back up top, and we're going to look at this diene. And you can see I have the dienes kind of color coded, one in red and one in blue. So we're going to start with the the one in red. We'll call it, let's call that alkene 1. And then we'll call this one alkene 2. All right, so we're going to start with alkene 1. Make that that black so I can keep the colors. All right, so we're going to take that plus HBr. So this is going to attack here like so, just like a simple addition of HX to an alkene. It's the same reaction. The difference will be the intermediate. Under normal circumstances, if this wasn't conjugated, that tertiary intermediate that you would get on this carbon right here will probably be your, or not, it's not probably, that would be where your carbocation was, right? But the fact that this is a conjugated diene, when it reacts, the cation that you get, the carbocation that you get is going to be here because it's the allylic carbocation that's your intermediate. Right, that allylic carbocation is common to both products that you're going to get. So we're doing this at 0 degrees Celsius. Right, you're still going to get both products. Where bromine, let me move this. Where bromine can attack directly at the plus charge. Right, and it'll give you this. Our bromine is there. That's double group doesn't move, and then this alkene is still here, right? So that's one product, and then the other. So this is the major at 0. We call this the kinetic product, all right? But then bromine can also attack here. And shift that double bond over. Or you can draw the resonance form and show the plus charge on the other carbon. Either way is fine. But that's going to give you this product where the double bond gets shifted over to here. And then the bromine ends up here. Right? So this is minor product. This is 1,4, and we'll call that thermodynamic product. Right, so anytime you're doing this addition of HX conjugated diene, you're going to get you're going to have that temperature. Right, so it's that temperature dependence is a characteristic of this reaction. Right, so if we use alkene 1, the red one, then these are the two products. And at 0 degrees, the major is going to be, let's label them. This is A and this is B. So at 0 degrees, A is major and B is minor. If we increase the temperature, we can even go up. I'll follow the example. It said 37. We can, if we go up in temperature, then A will become minor. And I'll explain that after we finish the example, like why you see that observation or why you observe that. All right, so you increase temperature, then the 1,4 product becomes predominant, and then the 1,2 product becomes the minor product. All right, so it's temperature dependent. All right, let's look at the other alkene. So we use alkene 2. So if I could just steal this from up here. All right, so it'll be this plus HBr. So when alkene 2 attacks HBr, and again, this is not a new reaction. This is, if you think back to part 1, when we started talking about alkenes, this was like the first reaction we learned, where you have an alkene and it acts as a nucleophile when you add HX to it. All right, so if I do that, where's my carbocation going to be? What is it going to look like?
It's going to be, you're going to have a plus where that blue double bond was. It's going to be a positive charge.
Yes. On which carbon?
The one to the right. Wait, yeah, the one to the right of it.
This one?
Yeah.
Okay, great. Yeah, you're absolutely right. Because again, the intermediate has to be an allylic carbocation, right? That's the hallmark of this reaction, is that when you add HX to it, right, you get an allylic carbocation as the intermediate. So the plus charge is going to be right here. It's a common intermediate to both products. Right, and then it's that. And then again, we'll see this temperature dependence at 0 degrees, right? Bromine attacks directly at that carbon. Right? So that's going to be your 1, 2. And at 0, this is major. We'll call it product C. Right? What would D look like?
Bromine will be at 4, carbon number 4.
Would that be right here? Right, so the other product would be if bromine attacked here at that carbon. Right, that's one. This would be your 1, 4 product. This would be your 1, 2 product. And at low temperature, this is major. At high temperature, I'm sorry, low temperature, this is minor. Right, and then if you increase the temperature to in this case, for this example, 37, right? C becomes minor. And then this becomes major. All right. Any questions about that example? So the point is to kind of show the temperature dependence. Like at 0 degrees, you're going to get a product that we consider what we call the kinetic product. It may not be the most stable, but it's the product that's formed the fastest. And then at higher temperatures, you get what we call the thermodynamic product. It's not as formed as fast, but the stability is greater than the kinetic product. All right, we're going to talk about that in terms. I know if you watched the video, you saw the energy diagram explanation for kinetic versus thermodynamic, but let's talk about it here. Let me add a page here, and then we can discuss the thermodynamics of it. All right, so let's go back to here. It says of both products from the reaction done at 0. So it's telling you that these are the kinetic products, or warm to 40. The product distribution changes and the kinetic product is converted into the thermodynamic product. Using a major product from the reaction done at 0, propose a mechanism for how this might occur. All right, so again, at 0 degrees, these are the two products that we get, right? Depending on which alkene reacts, we either going to get that or this. All right, so those are my two major products at low temperature. So those are drawn down here, right? So the question is, how can I convert between that and what we call the thermodynamic product, or the product that is going to give you more stability, right? And the key is right here, right? You have to warm it up to 40 degrees or warm it up from 0 in order to put more energy into the system so that this can happen, right? Like this inner conversion can happen. So if you look at the kinetic product, how can I go from here to here? Like what arrow could you show going from the kinetic product back to the intermediate? Just look at what happened.
You can break that bromine bond.
Break the carbon bromine bond. Yes. Yeah. Put some electrons on here. Right. So if I broke that like so, it would take me back to that carbocation. And the thing about it, we've seen this type of spontaneous bond cleavage before, haven't we? Like anytime when we talked about the SN1 or the E1, right? The first step was the loss of a leaving group. And so we see here, it's a similar type process where you can spontaneously lose bromine, but that's not going to happen until you start upping the temperature. And then now, how would we go from this intermediate to here? How would you show that?
By having bromine attack that double bond.
So bromine just coming in and attacking here, right?
Mm-hmm.
And shifting the double, let me fix that arrow. Shifting the double bond here. right? So if you start with the kinetic product and you raise the temperature, what you do in essence is you are also creating conditions for equilibrium. So you can go from the kinetic product back to the intermediate, and then from the intermediate to the more stable product. I'm gonna show you the energy diagram in a second, how that's possible. All right, and then here you can do the same thing. It will be a similar mechanism, right? You would lose bromine to get back to the intermediate, and then that intermediate can then get attacked like so, right, to give you the thermodynamic product, right? But the reason this is possible is, again, because of the increased temperatures. It says that you have to warm it to 40 degrees Celsius. So this is redundant if you saw the video, but it's also reinforcing what you saw. So under kinetic conditions, for low temperature, right, you have your intermediate, which is here, which is what you're starting with. Obviously, there's a step to get to the intermediate, but for the purposes of this discussion, the first step will be considered fast, right? So there's the intermediate attack on the intermediate that's rate determinant. So that's what we care about. So you have your intermediate, and that intermediate can get converted into, I don't want that to look like that. One product here, or one product here, right? And this is time. And then on the y-axis, energy. Right, so if you notice, this is the thermodynamic product. And then this is the kinetic. Right, the reason we call it the kinetic product is because it's formed faster. Look at the activation energy compared to the right. So this is the activation energy for the kinetic product. And when you compare that to the activation energy for the thermodynamic, I'll just draw it out here. Right, it's lower. So lower activation energy is going to lead to a faster rate of reaction. Right. So when you have your low temperature conditions, this is what you set up. So the kinetic product at under these conditions is irreversible. Right, there's no equilibrium. Right, so the lowest, the product with the fastest rate is going to predominate. And that's not to say that you can't make the other product, because you obviously will see both, but the percentages will be different, right, based on these conditions. So this is low temperature kinetic conditions. It's all irreversible. So once you go from the intermediate to the product, you can't go back because there's not enough energy available to go back. All right. The lower the temperature, the less energy is available. And then if you look at the same reaction under what we consider for this reaction, thermodynamic. Let me just rewrite that. Conditions, right, where you have, just going to say increased temperature. All right, and we can even use the same chart. So under thermodynamic conditions, it's the more stable product that's going to predominate. And the reason we can say that the product is more stable is because you can see if the energy is increasing in this direction. Right, energy is increasing that way. You can see the thermodynamic product is lower in energy than the kinetic product, right? So it's more stable. And then the other part of this is that this is now reversible. You can establish equilibrium. And there's enough energy right to cross the barrier that's there to get to your thermodynamic product. Because again, at increased temperature, the energy of the system is also going to be increased. So the activation energy to get to the thermodynamic product is doable now, right? It's more accessible. What also happens though, all right, what also happens is now the kinetic product, right? When we say equilibrium is established, but the kinetic product, there's enough energy for it to go back and get converted into the intermediate under these conditions. So at increased temperature. So there's enough energy for the kinetic product to be converted back into the intermediate. I'm going to abbreviate intermediate for space. Then it can also, once you go back to the intermediate, you can then convert it into the thermodynamic product. All right. So that's how this works, right? So you have both of your products are temperature dependent. One is, again, going to be formed faster than the other. And then you also have one that's more stable than the other. So depending on the temperature, That's going to determine which one of those two products gets formed the fastest. So at low temperature, your kinetic product is going to predominate. At higher temperatures, your thermodynamic product is going to predominate. But under these conditions, you're going to get both. The extent of product formation is going to change though. So under thermodynamic conditions, you'll get both products, but again, the 1,4 product is going to predominate. And then under kinetic conditions, you'll get both products, but it's the 1,2 product that's going to predominate. All right, any questions about this section? Any questions about the mechanism, about the arrows, about anything? All right. So let me give you, let's do another example. I had some more, sorry about that. I thought I had some more questions in this handout. Obviously do not. I can just add one in. Well, so let's work through this example. One last example, and then we're gonna actually go ahead and start Cyclo Addition. And then when we come back on Friday, we'll continue with Cyclo Addition. All right. And for this example, we're only going to use let's just use this alkene right here. Right, we're not going to use the other one. All right. So how would this reaction happen? First of all, what would the intermediate look like? And what would the two products look like? If I use the alkene that's highlighted in green.
So you would split that hydrogen bromine bond,
Okay.
and
Then
then
attack it like that. All right. So what would the intermediate look like?
you would have a positive charge where that highlighted alkene is.
On which carbon?
Like right down the yeah,
Right
that
here?
one.
Okay, good. Yeah. Right. It's got to go through
Allylic
the
carbon.
little carbocation. That's exactly right. It's got to go through that. All right. So that's my intermediate. And then I have a bromine here that can attack it. All right. Where is it going to attack?
At that positive charge.
And we're at 0 degrees. So attack
So that's
here. Yeah. All right. That's going to give me one product.
And that would be our major product, right?
Yes, at 0. Yes, that's exactly right. All right. Oh. Yep. And then what about the other product?
The minor product, the bromine would just attack at That would it attack at that other allylic site? Yeah.
Right here?
Mm-hmm.
Yes. And then that's gonna move the
That double bond
double
over.
bond down to here. Yes.
Mhm.
Right, so you'll get a second product. Where bromine is here, like that. But this is, again, at 0, this is gonna be major. Right, so this is gonna be my kinetic. And this is gonna be my thermodynamic product. Excellent. All right. So the other reaction that we're going to talk about with these conjugated dienes is what we call Cyclo Addition. So it's a totally different, Let me add a page. Make sure I'm in the right place. Right. So Cyclo Addition is a reaction that conjugated dienes undergo, where you start with a conjugated diene, like this one. You react it with some pi system, either alkene, or it can even be an alkyne. I'll show you that too. Right, and what you end up with is a 6-member ring. That's why we call it Cyclo Addition, because you get a cyclic product. And within that 6-member ring, you have a pi bond. The pi bond gets shifted over. I'm gonna show you the mechanism and all that. All right, so here will be the same, well, similar, not the same. Right, so you'll get a cyclic diene if you use an alkyne, if you get a cycloalkene if you use a alkene. All right. So this cyclo addition is what we call a 4+2 cyclo addition. Right. It also is a name reaction. We call it the Diels-Alder reaction. Right, Diels-Alder reaction. So it's a 4+2. It's what we call, it follows what we call a pericyclic mechanism. All that means is that the electrons move in a kind of like in a circuit. So there are specific atoms that are involved in this cyclo addition. And I'm gonna show you the mechanism, and then it'll make sense to you, make more sense. All right, so it's called what we call pericyclic, and it's concerted. Right, and the outcome is always a 6-member ring, because if you're doing a 4+2, right, you're going to get a 6-member ring. Just think about it that way. All right, so the mechanism it's a fairly simple mechanism. I like to number the carbons to help you keep track of what's happening. All right, and let's do this so I can explain another aspect of this. So let's say 1, 2, 3, 4, 5, 6. right? So what you're going to end up with you're going to end up with a bond between 4 and 5. You're going to end up with a bond between 1 and 6. And then you're going to shift the pi bond that's between 1 and 2 to here, right? And the way you do that is when you put the arrows in, right? This pair of electrons is going to attack here. This pair is going to attack here. And then this pair of electrons and that pi bond will get shifted down like that. All right, so your product, and let me show you another aspect of this while we're talking about it. So your product is a 6-member. That's the core of a 4+2 cyclo addition, is the formation of a 6-member ring. So you got a 6-member ring there. All right, let's put the numbers back in. That's 1, 2, 3, 4, 5, and 6. Right, so between 2 and 3, you can see the arrow here. So I need to put a pi bond between 2 and 3, like that. And then on 5 and 6, I had substituents. I had a methyl group on 5 and 6, but the methyl groups are trans to one another because that's a trans alkene. Right? Are y'all following the fact that that's trans? Let me fix this arrow. I don't like how that looks. Right? So the fact that 5 and 6 are trans, they also in the star material, they also have to be trans in the product. So I'm gonna make 1 on a wedge, and I'll make 1 on a dash, like that. Are y'all following? So
Yes.
Trans,
Yes.
and then they have to also be trans over here. Because the reaction is what we call stereo specific. You have to maintain the stereochemistry of what we call the dienophile, right? So this is my diene. And then over here, the other star material, which is either, it could be an alkene or alkyne. This is what we call the dienophile. Right? So whatever your dienophile stereochemistry is, whether it's cis or trans, it has to be maintained because the reaction is stereospecific. All right. So anytime you have a 4 pi system and a 2 pi system, when you react them together, the orbitals are going to overlap and you're going to get a 6-member ring. So on Friday, we're going to talk about a little bit, the mechanism in a little bit more detail. We'll talk about the molecular orbital aspect of the mechanism. We kind of touched on molecular orbital theory already. So we're going to come back and talk more about that on Friday and how it affects the Diels-Alder and the reactivity. All right, so we're going to stop here and we'll pick this up on Friday.
Thank you. Have a good day.
All right, y'all take
Thank
care.
you. Have a good one.